Hello guys, in this video I'm gonna solve binary search tree problem. Implement a node class to create a binary search tree. The constructor should initialize values data left and right. But before solving this problem, let's define what is a binary search tree. As you can see, here is a binary search tree. So the binary search tree is a tree, but the difference, the distinguished feature is that for each node there are at max 2 children, and the left children is always less than the root node. For example, here 3 is less than 8, and the right child is greater than the root node, the value of the root node, which is here is 10 greater than 8, and so on for every node. We can the rules apply the same. So as you can see here, 1 is less than 3, 6 is greater than 3, and one thing to notice here is no nodes on the left. As you can see, if we look at 8, as you can see, there's no nodes, no single node in the left side of the 8 is greater than 8. As you can see, 1, 3, 6, 4, 7, they're all less than 8. The same here on the right, all nodes are greater than 8. So in order to insert a new node to the tree, the binary search tree, we need to as you all know, the tree is determined by root node, so we always start from this root node. For example, if we want to insert 9, right? If we want to insert 9 into this tree, how can we do it? 9 we compare with 8, which 9 is always 9 is greater than 8, so it should be on the right. Okay, we are currently sitting at 8. We move to 10. Now, how about 9, 10? 9 is less than 10, so 9 should be on the left 10. And currently 10 has no left child, so we simply point the left to the new node, which has value 9. So that's how adding a new node to binary search tree. So let's come back to our program. Implement, but first we need to implement a constructor. A node contains a data, left pointer and right pointer, but let's initialize with no. If there's nothing provided, it will be no. So we assign to the property this dot left equal to left, this dot right equal to right. Okay. Implement this insert method for the node class. Insert should accept an argument data, then create an insert. Create and insert a new node at the appropriate location in the tree. Okay. So as I said, we need to start from the root node, right? And at each node, we want to check if the new node, where the new node should be put in, whether it is on the left side or on the right side, right? So for that operations, we probably want to run into loop until we find a appropriate position for the new node. Okay, so how about creating the new node first? New node equal to new node. The new node has data with left and right node. We'll run into a loop something like here until we find the appropriate position, and in order to traverse the tree to find the position, we probably want to store a working pointer that points to the current node that we're sitting in. Let's start with current. That's point to this node. We are sitting in a node, class node, so this is pointed to the node, right? And it is actually the root node. So we want to run into a loop. And be careful with while true, because it may run into an infinite loop if you don't break it somewhere. Let's say we probably want to compare current dot. Current is a node. Current has data. We're going to compare the data with the data of the new node, right? What are the cases we have here? If the data is greater than current node data, then it should be on the right, right? Right. For example, 8. We insert 8 into this tree. We come first compare 5 with 8. 8 greater than 5, so 8 is on the right. We move to 9. 9 is less than 8 is less than 9, so 8 should be on the left of 9, and left of 9 is no, so we should attach the new node to the left side of the 9. So probably the two cases here, right? If the data greater than the data of the current node, it means it's on the right, but there's two cases here. The right is no and the right is not no, right? In case the right is not no, current.right, it means you want to go right. You want to continue traverse the tree on the right side, right? Current equal to current dot right. And if it is not the case, this one is not true, return to true. And else if data still current the data, if this is not true, as you can see, these two expressions, conditions have the same data as current data, and if this is not true, then it means when it comes here, the current dot rise now. We only run into this loop if current dot rise now. And if current dot rise no, we want to attach current dot rise to the new node. Okay. Then probably want to break here because we already adding the new node to the tree. So what else? What is else if data is less than or equal to current data, and we have current lab. Then we want to move on to the lab. Move on to the lab node, current node lab, and else if data with the less than or equal to current data, we want to current lab equal to if you run into here, it means current lab is null. So we want to attach a new node to current lab. New. So if we exit the loop, it means we want to break here, right? Break. If we exit the loop, it means either we run into this case or this case. So let's run a test. Just BSD. Hopefully it will work. Alright, we have two tests because two failing tests are because of this method we haven't implemented yet. Alright. Contains now our goal is to let's add one more level here. Paste it down here. Alright, so now we want to check if the if it contains 8. So the idea here is the same. We also need to, in order to check if a node is contained in the tree, we also need to traverse the tree to find where it is in the trees, because the tree is binary search tree, so either left or right. We want to check if the data passing in with the data kernel starting at the root node, and right, there are two choices, only left or right. So yeah, in the case we couldn't find the data, we couldn't find the node with the same value as data, then we should return no, right? For example, if it's 7, as you can see, there's no 7 in the tree, so it should return no. So if 7, we start in root node 7, is on the right, for example. Okay, we're here. 7 is less than 9, so it's on the left. 7 is less than 8, so it's on the left. But the left is no, so we just return no. Okay, we are stop traversing because we reach the leaf node of the tree. Let's say it's the same here. As we want to traverse the tree, we need to keep a working pointer, which initially points to the root node, which is this keyword, because we're sitting in the node class. So if the data equal to current dot, if the data equal to current dot data, just return current. But definitely we want to do it in a loop, right? We probably don't want to. We only want to run the loop if the current node is not null. So if we exit the loop, it means current is null. We can find it, so we want to return current. Current is null. Let's be explicit. If we exit the loop, we return null. So if data equal to current, return the current node, right? So what is the other case? If data greater than current data and else, it means data less than current data. If this is case, we want to go to the right of the tree, current right. This one is current left, because there's only one statement, so let's clean it up. Okay. Alright, so let's run test. Awesome. So thank you for watching. See you in the next video.